So, could the most powerful computers we can even imagine pull off the greatest digital heist in history? That's the question today. We're going to dive into this looming battle between Bitcoin's cryptographic fortress and the insane code-breaking power of quantum computers. We'll break down the science, the real risks, and what's actually going on behind this digital showdown.
I mean, wow, that's a pretty terrifying thought, right? Especially for anyone in the crypto space. It basically paints this picture of a digital doomsday, where some new supermachine just flips a switch and turns off Bitcoin. Now, this is exactly the kind of statement that grabs headlines, for sure. But, our job is to dig a little deeper than that.
So, is it really that simple? Is this a genuine threat that's right around the corner? Or is it just a classic case of, well, fear, uncertainty, and doubt, what everyone in the space calls FUD? Okay, let's try to separate the science fiction from the financial reality and figure out what the actual risk is here.
All right, to really get the threat, we have to understand the weapon itself. And look, quantum computers are not just faster versions of the laptop you're using. That's the key thing to get. They operate on completely different principles of physics. And it's those bizarre principles that give them this unique and pretty dangerous power against the encryption we all rely on.
So the main weapon in this whole theoretical attack is something called Shor's algorithm. It's actually been around since the 90s, believe it or not. And it's basically a quantum recipe for breaking the exact kind of math that underpins most of the internet's security. And yup, that includes the digital signatures that prove you own your Bitcoin. Think of those signatures as a unique, unbreakable digital lock. For your computer or any classical computer, finding the key is basically impossible. But for a quantum computer running Shor's algorithm, well, it's not a matter of if, it's a matter of when.
Okay, so where does this crazy power come from? Well, it's all about a fundamental difference. A classical computer thinks in bits, right? Simple, clean, zeros and ones. But a quantum bit, a qubit, this is where it gets a little mind-bending. It can be a 0, a 1, or both at the same time. It's a state called superposition, and this allows a quantum computer to explore a massive exponential number of solutions all at once. That's the magic trick that Shor's algorithm uses to just shatter encryption.
Okay, so we've got this super powerful code-breaking tool. The first place people's minds usually go is Bitcoin mining. It makes sense, right? Could a quantum computer just steamroll everyone, outmine the entire network, and take it over?
So at its core, mining is really just a brute force guessing game. You have miners all over the world racing to find a very specific number that solves a puzzle. The first one to find it, they get to add the next block to the blockchain and, of course, claim the reward. It's all about raw, brute force hashing power.
Now, for this type of problem, this giant find the needle in a haystack search, quantum computers have another tool in their belt. It's called Grover's algorithm. Now, it doesn't just instantly solve the problem like Shor's does for signatures, but it offers what's called a quadratic speedup. What does that mean? Well, in really simple terms, to get 1,000,000 times speedup, you only need a machine that's 1,000 times faster. And yeah, that sounds like a total game changer.
But, and this is a big but, this is where the theory smacks right into reality. For decades, we've been building these hyper-specialized machines called ASICs. They're designed to do one thing and one thing only: solve Bitcoin's hash puzzle at lightning-fast speeds. And when you look at the numbers, even with that fancy quantum speedup, the projected speed of a near-term quantum computer is just so slow. It can't even get in the same ballpark as a modern ASIC, not even close.
So, what does this all mean? It means when we're talking about mining, the quantum threat is, well, it's pretty minimal for now. The research is pretty clear on this. Even in 10 years, quantum computers probably won't be able to compete with the raw, specialized speed of classical hardware. So, the Bitcoin network itself, it's not at risk of some hostile takeover. Phew.
Okay, but hold on. That doesn't mean we're totally in the clear. The real danger here isn't about taking over the network. Nope, it's about something much simpler. Outright theft. A targeted, surgical heist that could happen in the blink of an eye.
Here's the playbook for how it would work. Step 1. You decide to send some Bitcoin, so you broadcast your transaction to the whole network. That broadcast reveals your public key. For an attacker with a quantum computer, that's the starting pistol. Step 2. They take that public key and, using Shor's algorithm, they work backward to figure out your private key, the keys to the kingdom. Step 3. With your private key, they whip up a brand new transaction sending your money to their wallet. And finally, step 4, it's a race. They broadcast their fake transaction, trying to get it confirmed by miners before your real one is. And this whole heist, this entire operation, has to happen on a very tight schedule. There's a ticking clock. See, on average, it takes about 10 minutes for a new block to be mined and for your transaction to get locked in and secured on the blockchain. So that's the attacker's window of opportunity. Roughly 10 minutes to see your key, crack it, and hijack your funds before it's too late.
So, obviously, the billion-dollar question is, how fast could a quantum computer actually do this? Well, some startling research from Agarwal and his team give us a number, and it's a little scary. Based on some pretty optimistic projections for how quantum hardware is developing, they estimate that by 2027, a quantum computer could exist that can break Bitcoin's digital signature in under 10 minutes.
Whoa, okay. 2027 sounds alarmingly close. I get it. But before we all start to panic, we need to take a deep breath and have a serious reality check. Because building a quantum computer powerful enough to actually pull off this heist, it's literally one of the hardest engineering challenges humanity has ever faced.
You know, as researcher Craig Wright points out, the hype around this stuff often runs way ahead of the actual progress. For decades now, a big breakthrough has always been just around the corner. The fundamental nuts and bolts problem is that these quantum systems are just incredibly fragile.
The slightest little disturbance from the outside world, a tiny vibration, a change in temperature, can make a quantum state just collapse. It's a thing called decoherence. This noise creates a ton of errors. So the solution that people are working on is to bundle thousands, literally thousands, of these unstable physical qubits together just to create one stable, error-corrected logical qubit. And here's the kicker. A machine that could break Bitcoin would need thousands of these logical qubits. We haven't even reliably built one yet.
And then there's the money. I mean, let's talk economics. Even if you could magically build this machine, the costs are just staggering. We're talking over $1 billion just to build it, and then maybe $150 million a year just to keep the lights on. So for this to make any sense, an attacker would need to find and crack addresses holding more than $12.5 million each, and they'd have to do it over and over. Right now, the biggest known exposed address holds just a bit more than that. The attacker would need to find hundreds of targets like that, and they just don't exist.
But you know what? Even if we just ignore all those massive technical and economic hurdles for a second, it turns out Bitcoin has a very simple built-in defense that works right now, today.
Okay, get this. Your Bitcoin address, that long string of letters and numbers you give people so they can pay you, is not your public key. It's actually a hash of your public key. Hashing is a one-way street, cryptographically speaking. It's like putting a cake's ingredients into a blender. You can easily blend everything to get a smoothie, but there's no way you can look at that smoothie and perfectly figure out the original recipe. And what this means is, as long as an address has never been spent from, its public key stays hidden and totally safe from Shor's algorithm.
And this right here is probably the most important takeaway for any Bitcoin user. If you reuse an address, let's say you spend from it and then get funds sent back to that same address later, your public key is now permanently stamped on the blockchain, forever. It becomes a sitting duck, just waiting for a powerful enough quantum computer to come along someday. The best practice, and this is how Bitcoin was designed to be used, is to never, ever reuse addresses. Create a fresh one for every single payment you receive. If you do that, your public key is only ever exposed for that brief 10-minute window while you're waiting for your transaction to get confirmed. It massively shrinks the attack surface.
So where does all this leave us? Well, this isn't really a story with a neat and tidy ending. What it is an ongoing technological arms race.
On one side of this race, you've got the code breakers. They're the scientists and engineers pushing the absolute boundaries of physics, trying to build more powerful, more stable quantum computers. And on the other side, you've got the code makers. They're the ones improving security practices, getting people to stop reusing addresses, and, this is a big one, actively developing brand new post-quantum signature schemes that would be safe from even the most powerful theoretical quantum attacks.
So, see, the big takeaway here isn't that Bitcoin is just going to expire the day a powerful quantum computer shows up. The real question is, who's going to win this race? Will the code breakers build their ultimate machine faster than the code makers can build up our defenses? It's a huge question, and honestly, the security of our entire digital future might just depend on the answer.